Hello everyone. So, today we will solve few example problems of convective heat transfer in external flows. So, we have already covered few lectures in last two modules related to convective heat transfer in external flows, and let us apply those knowledge to solve some numerical problems. So, let us discuss the first problem. For laminar boundary layer flow over a flat plate with air at 20 degree centigrade and 1 atmosphere, Prandtl number is equal to 0.709, the thermal boundary layer thickness delta T is approximately 13% larger than the velocity boundary layer thickness delta. Determine the ratio delta by delta T if the fluid is ethylene glycol, Prandtl number is equal to 211 under the same flow conditions. So, you can see for a given condition delta by delta T is given. Now, we need to find the delta T for ethylene glycol where Prandtl number is given. Okay. So, we know that for external flows, if the flow is laminar, then delta by delta T is equal to Prandtl number to the power n. So, this n for air we know it is 1 by 3, but for this particular case we need to determine from the given condition. So, we know that for laminar flow delta by delta T is of the order of Prandtl number to the power n. Okay. So, here you can see the first fluid is air, and for air it is given that your delta T is approximately 13% larger than delta. Okay. So, you can write delta T is equal to 1.13 into delta from the given condition. So, you can see that delta by delta T is 1 by 1.13. Now, you have the same flow conditions. Okay. So, under this now for air we have to find what is the n. Okay. So, you can see here delta by delta T is equal to 1 by 1.13. So, if you put it here, so we will get Prandtl number to the power n is equal to 1 by 1.13. Okay. So, now you can find Prandtl number is given as 0.709. Okay. So, you can see 0.709 to the power n is equal to 1 by 1.13. So, from here you find n you will get as 0.355. Okay. So, for ethylene glycol it follows that delta by delta T will be approximately Prandtl number to the power n is 0.355 because you have the same flow conditions. Okay. So, n will be same. So, now Prandtl number is different. Okay. In this case Prandtl number is 211. So, if you put that, so you will find delta by delta T will be 211 to the power 0.355. So, hence you will get delta by delta T as 6.69. So, you just notice here that for air delta by delta T obviously is less than 1. Okay. You can see here it will be less than 1, but in case of ethylene glycol delta by delta T is greater than 1. So, if you plot the hydrodynamic boundary layer and thermal boundary layer, then you will see for air if it is your boundary layer hydrodynamic boundary layer, then your thermal boundary layer will be higher than the hydrodynamic boundary layer. Okay. So, this is your delta, this is your delta T, it is for air. Okay. And if you consider ethylene glycol, then if it is flat plate, then in this particular case this will be your thermal boundary layer and hydrodynamic boundary layer will be higher, because Prandtl number is greater than 1. Okay. So, Prandtl number in this case it is 211. Okay. You have ethylene glycol, okay, and this is your Prandtl number 0.709. Okay. So, let us take the second problem. Atmospheric air U infinity is equal to 15 meter per second, T infinity 15 degree centigrade flows parallel over a flat heated surface, which is to be maintained at a temperature of 140 degree centigrade. The heated surface area is 0.25 meter square and the airflow is inducing a drag force of 0.25 Newton on the heater. Calculate the electrical power required to maintain the prescribed surface temperature. Use Prandtl number is equal to 0.7, rho is equal to 0.995 kg per meter cube and Cp is equal to 1009 joule per kg Kelvin. So, in this particular case you can see your surface temperature is to be maintained at 140 degree centigrade. So, if you consider the flat plate, okay, so the drag force acting on this flat plate is 0.25 Newton, it is given, okay, and your surface temperature Tw is your 140 degree centigrade and area of this plate is given as 0.25 meter square, okay, and your U infinity is 15 meter per second, which is your free stream velocity, free stream temperature T infinity is 15 degree centigrade, okay, and you need to find what is the electrical power required, okay, Q, to maintain the surface temperature as 140 degree centigrade. Okay. So, we know the drag force acting on the plate. So, we will be able to calculate the shear stress acting on the surface. Okay. So, shear stress, okay. So, this is your average shear stress tau w is equal to F d by A is equal to 0.25 Newton is your F d, area is 0.25. So, it is 1. Okay. So, if it is a average shear stress, so just I will denote with tau bar. Similarly, the coefficient of drag Cf you can write tau w divided by half rho u infinity square. Okay. So, it is due to shear and tau w is 1 divided by half, density is given 0.995 into u infinity square. Okay. So, u infinity is 15 square. So, if you calculate it, you will get as 8.93 into 10 to the power minus 3. Okay. So, now you know Cf. So, we will calculate the heat transfer coefficient using Reynolds analogy. Okay. So, Prandtl number you can see it is of the order of 1. So, you can use this Reynolds analogy to calculate the average heat transfer coefficient. Okay. So, you know that Stanton number is equal to average heat transfer coefficient divided by rho into u infinity into Cp, okay, and this you can relate with Cf divided by 2 Prandtl number to the power minus 2 by 3. Okay. So, from here you can calculate the average heat transfer coefficient H bar as half into rho u infinity Cp Cf Prandtl number to the power minus 2 by 3. So, half into density is 0.995 into u infinity 15, Cp 1009, Cf 8.93 into 10 to the power minus 3 and Prandtl number is 0.7 to the power minus 2 by 3. So, if you calculate, you will get the average heat transfer coefficient H bar as 85 watt per meter square Kelvin. So, now we have calculated the average heat transfer coefficient, you know the total heat transfer area. So, you will be able to calculate the heat transfer rate. Okay. So, that is your using Newton's law of cooling, you can write as H into A into T W minus T infinity. So, Q will be your just H bar into A into T W minus T infinity, where H bar is 85, area is 0.25 into T W is 140 minus T infinity is 15. Okay. So, if you calculate it, so you will get Q as 2.66 into 10 to the power 3 watt, okay, or Q is equal to 2.66 kilowatt. Okay. So, this is the electrical power required to maintain the surface temperature at 140 degree centigrade. So, let us discuss the third problem. Engine oil at 100 degree centigrade and a velocity of 0.1 meter per second flows over a top surface of a 1 meter long flat plate maintained at 20 degree centigrade. Determine the velocity and temperature boundary layer thickness at the trailing edge. Also calculate the total drag force and heat transfer rate per unit width of the plate. The properties are given here. So, you have one flat plate. Okay. So, where u infinity your free stream velocity is 0.1 meter per second, T infinity is 100 degree centigrade. Okay. So, this engine oil is flowing over this flat plate. Okay. Now, the length of the plate is given, L is 1 meter, x is measured from this leading edge, the T W is 20 degree centigrade. Now, we need to determine the thermal boundary layer thickness delta T and your hydrodynamic boundary layer thickness delta. Okay. So, you can see Prandtl number is 1081. So, it is much greater than 1, obviously delta will be greater than delta T. Okay. So, first let us check whether flow is laminar or not. So, we will calculate the Reynolds number from the given data. So, Reynolds number R E based on the length L is u infinity L by nu, where u infinity is 0.1, L is 1 divided by the kinematic viscosity 86.1 into 10 to the power minus 6. Okay. So, if you calculate it, you will get as 1161. Okay. So, you can see it is a laminar flow. Okay. So, now you know for flow over flat plate delta by L as 5 by root REL. Okay. So, from this you can calculate the hydrodynamic boundary layer thickness delta as 5 into L is 1 divided by 1161 to the power half. So, if you calculate this, you will get 0.147 meter. Okay. And we know delta by delta T varies as Prandtl number to the power 1 by 3. So, delta T will be your delta into Prandtl number to the power minus 1 by 3. So, delta you know 0.147, Prandtl number 1081 to the power minus 1 by 3. If you calculate, you will get 0.0143 meter. Okay. So, delta and delta T now we have found. Now, we need to find the total drag force and heat transfer rate per unit width of the plate. So, now your CF you can calculate as 1.328 divided by root REL. Okay. So, this is the expression we have already derived, okay, for flow over flat plate. So, you can see it will be 1.328 into 1161 to the power minus half. Okay. So, this is your Reynolds number to the power minus half. So, you will get 0.0388975. So, now you will be able to calculate the shear stress. Okay. So, shear stress will be just CF into half rho infinity square. Okay. So, you will get as 0.38975 into half into density 864 kg per meter cube into u infinity square. So, 0.1 square. So, if you calculate it, you will get it as 0.16837. Okay. So, now drag force per unit width you will be able to calculate as drag force per unit width. Okay. So, d unit width means perpendicular to this board. Okay. So, in that direction. So, that is per unit width we are calculating and we are just prime we are telling, okay, per unit width as. So, it will be the area into tau, right. So, tau into area. Okay. So, what will be your area? Okay. So, per unit width we are calculating. So, it is 0.16837 into area. So, area is length into width. So, per unit width we are calculating. So, into 1. So, we are considering only top surface of the plate, okay, because it is written that flows over the top surface. Okay. So, it will be 0.16837 into the area we are considering on the top side. So, it is L into 1. So, it is 1. Okay. So, you will get as 0.16837 Newton per meter. Okay. Now, we need to calculate the total heat transfer rate. Okay. So, Nusselt number you know relation, okay, for the Nusselt number average Nusselt number you can write as H bar L into length divided by thermal conductivity as 0.664 into Reynolds number to the power half and Prandtl number to the power 1 by 3. So, this relation we are using because you know that Prandtl number is much greater than 1, 1081. So, it will be Reynolds number to the power half into Prandtl number to the power 1 by 3. So, from here you just calculate the average heat transfer coefficient. So, it will be 0.664 into Reynolds number you know 1161 to the power half, Prandtl number is 1081 to the power 1 by 3 is equal to 232.1985. So, heat transfer coefficient you will be able to calculate as 232.1985 into thermal conductivity 0.14 divided by L, L is 1. Okay. So, this will give us 32.51 watt per meter square Kelvin. Okay. So, now heat transfer rate per unit width you will be able to calculate. Heat transfer rate per unit width. Okay. So, q prime I am writing because per unit width we are writing. So, it will be just h bar L into area into T w minus T infinity. Okay. So, it will be 32.51 into area. So, we are considering only top surface, okay, one side of the plate we are considering, and so your area will be only 1 as we are considering per unit width into T w minus T infinity. So, it will be just 20 minus 100. Okay. So, if you calculate it, you will get approximately as 2600 watt per meter. Okay. So, what is the significance of this negative sign? Because we are calculating Q from the surface to the fluid, okay, because we have written T w minus T infinity, but Q is coming as negative, that means heat transfer is taking place from the fluid to the wall, okay, fluid to the surface. Now, let us discuss about the next problem. Here thermal conductivity as 0.0284 watt per meter Kelvin at a free steam temperature T infinity 20 degree centigrade is in parallel flow over a flat plate of length 5 meter and temperature T w at 90 degree centigrade. However, obstacles placed in the flow to intensify mixing with increasing distance x from the leading edge, and the spatial variation of temperatures measured in the boundary layer is correlated by the expression of the form T is equal to 20 plus 70 into e to the power minus 600 into xy, where x and y are in meters. Determine the local convection coefficient H as a function of x and evaluate the average heat transfer coefficient for the plate. So, in this particular case, the temperature variation with the coordinate x and y is given. So, from there you will be able to calculate the temperature gradient at the wall. Once you know the temperature gradient at the wall, you will be able to calculate what is the heat flux from the surface, okay, and then you will be able to calculate the local heat transfer coefficient. Once you know the local heat transfer coefficient, you will be able to calculate the average heat transfer coefficient for the plate. So, T, which is function of x and y, is given as 20 plus 70 into e to the power minus 600 into x y, where x and y are in meter. Okay. So, if you consider a flat plate, okay, L is 5 meter, your free steam temperature T infinity is 20 degree centigrade, your surface temperature T w is 90 degree centigrade, okay, and y is measured perpendicular to the plate and x along the plate, and your boundary layer thickness will be like this. Now, you first calculate the local heat transfer coefficient. So, H you know, this is your heat flux at the wall divided by T w minus T infinity. This is your local heat transfer coefficient is equal to Q w double prime means heat flux at the wall is minus K del T by del y at y is equal to 0, because at the wall divided by T w minus T infinity. Okay. So, the temperature is given here. So, del T by del y you can calculate as del T by del y as minus 70 into 600 x into e to the power minus 600 x y. Okay. So, now you see at del T by del y at y is equal to 0. Okay. So, at y is equal to 0, what will be your del T by del y? It will be minus 70 into 600 into x. Okay. You will be able to calculate the local heat transfer coefficient H as So, this is your minus and minus will be plus. So, it is k into 70 into 600 x divided by T w minus T infinity. So, H will be thermal conductivity K is given as 0.0284 into 70 into 600 x divided by T w is 90 minus T infinity 20. Okay. So, hence you will be able to calculate H as 17.04 into x watt per meter square Kelvin. Okay. X in meter. Okay. Now, you know the local heat transfer coefficient. Now, if you integrate over the flat plate, okay, and divided by the length of the plate will give you the average heat transfer coefficient. So, average heat transfer coefficient H bar you can write 1 by L integrate H 0 to L H into dx. Okay. So, you can see H is 17.04 into x, x you keep inside the integral, L is the length of the plate 5 meter, 0 to 5 x into dx. Okay. So, it will be 17.04 by 5 x square by 2, right, x square by 2 0 to 5. So, it will be 17.04 divided by 5. So, it is x square. So, 5 into 5 divided by 2. Okay. So, this 5 will get cancelled. So, you can calculate the average heat transfer coefficient H bar as 42.6 watt per meter square Kelvin. Now, let us take the next problem. An object of irregular shape has a characteristic length of 1 meter and is maintained at a uniform surface temperature 400 Kelvin. When placed in atmospheric air at a temperature of T infinity 300 Kelvin and moving with a velocity of 100 meter per second, the average heat flux from the surface to the air is 20,000 watt per meter square. If a second object of the same shape, but with a characteristic length of 5 meter is maintained at a surface temperature 400 Kelvin and is placed in atmospheric air at T infinity 300 Kelvin, what will be the value of average convection coefficient be if the air velocity is 20 meter per second. So, you have two irregular shape. Okay. So, if you see if those are geometrically similar, then you will be able to equate the non-dimensional number, Reynolds number and Nusselt number. So, let us take this irregular shape, let us say case 1. So, you have let us say one shape like this whose characteristic length L1 is 1 meter, T wall is 400 Kelvin, your V1 is 100 meter per second, T infinity is 300 Kelvin and Q double prime 1 is 20,000 watt per meter square. Now, if you consider case 2, you have second object of the same shape. Okay. So, it is of the same shape, but characteristic length is different. Okay. So, in this case your characteristic length is 5 meter, wall temperature is 400 Kelvin, your velocity is 20 meter per second and T infinity is 300 Kelvin. Okay. So, for a particular geometry, you know that the Nusselt number is function of Reynolds number and Prandtl number. Okay.
So, average Nusselt number is function of Reynolds number and Prandtl number. Okay. So, for case 1, what is the Reynolds number? Okay. Your Reynolds number based on the characteristic length is V1 into L1 divided by nu 1. V1 is 100, L1 is 1 divided by nu 1. So, it is 100 by nu 1. So, for case 2, what is the Reynolds number? Reynolds number based on the characteristic length L2, it will be V2 L2 divided by nu 2. Okay. So, V2 is 20, L2 is 5 divided by nu 2. So, it is 100 by nu 2. So, now you can see that since same year is used, okay. So, you will have Prandtl number 1 will be Prandtl number 2, okay. And you can see Prandtl number 1 is equal to Prandtl number 2. So, you will have nu 1 is equal to nu 2. So, you can see that Prandtl number 1 is equal to Prandtl number 2 because same year is used. Similarly, your for the same year your kinematic viscosity will be same. So, you can write Reynolds number L1 will be Reynolds number L2 from this expression. Okay. So, now as Nusselt number is function of Reynolds number and Prandtl number, but Prandtl number and Reynolds number are same for both the cases. So, Nusselt number also will be same. So, hence Nusselt number for 1 will be equal to Nusselt number for the case 2. Okay. So, you can write average heat transfer coefficient H1 L1 divided by K1 is equal to average heat transfer coefficient H2 L2 by K2. So, from here you can see you can write H2 will be in terms of L1 by L2 into H bar 1 and L1 by L2 it is 1 by 5. So, 1 by 5 means 0.2 into H1 bar. Okay. So, for case 1 the heat flux Q1 double prime is given. So, you can write Q1 double prime as H1 bar into Tw minus T infinity. Okay. So, you can write H1 bar is equal to Q1 bar by Tw minus T infinity. So, 20,000 divided by Tw is 400 minus 300. Okay. So, it will be just 200 watt per meter square Kelvin. So, once you know H1 bar, so now you will be able to calculate the H2 bar. So, for case 2, now you will be able to calculate your 0.2 into H1 bar. So, 0.2 into 200. So, it will be 40 watt per meter square Kelvin.
Let us consider now problem 6. First, let me read the problem. The forming section of a plastic plant puts out a continuous sheet of plastic which is 1.2 meter wide and 0.1 centimeter thick at a velocity of 9 meter per minute. The temperature of the plastic sheet is 95 degree centigrade, where it is exposed to a surrounding air, and a 0.6 meter long section of the plastic sheet is subjected to airflow at 25 degree centigrade at a velocity of 3 meter per second on both sides along its surface, normal to the direction of motion of the sheet. Determine the rate of heat transfer from the plastic sheet to air by forced convection and radiation. For air, thermal conductivity, kinematic viscosity, Stefan Boltzmann constant and Prandtl number are given. So, you can see this is the continuous sheet of plastic. Okay. So, the surface is maintained at 95 degree centigrade and air is flowing perpendicular to this direction of this sheet. So, this is your 3 meter per second
and air velocity is 3 meter per second and temperature is 25 degree centigrade. And the plastic sheet is having this velocity 9 meter per minute, and you can see the thickness of this plastic sheet is 0.1 centimeter, then 1.2 meter wide. So, this is your 1.2 meter wide, and it is having 0.6 meter long section. So, let us say that this is your 0.6 long section. Okay. So, now first let us calculate the Reynolds number and see whether the flow is laminar or turbulent. So, Reynolds number, okay, based on the width, because flow is taking place in this direction. So, in this direction you can see, if you consider this is a flat plate, then length of the flat plate will be 1.2 meter. So, REL will be just UL by nu, where U is the air velocity. So, this is your 3 into 1.2 meter divided by nu is given here. So, 1.896 into 10 to the power minus 5. So, if you calculate the Reynolds number, it will come as 1.899 into 10 to the power 5, and you can see the flow is laminar. Okay, because you know that if it is less than 5 into 10 to the power 5, then the flow is laminar. So, now we can use the Nusselt number relation for the range of Prandtl number. .6 less than equal to Prandtl number less than equal to 15, and you know here Prandtl number is 0.72. So, obviously, we can use this average Nusselt number relation as 0.664 REL to the power half Prandtl number to the power 1 by 3. So, from here you will be able to calculate the heat transfer coefficient. So, if you calculate the Nusselt number, putting the value of Reynolds number and Prandtl number, it will be 0.664, REL is 1.899 into 10 to the power 5 to the power half, and Prandtl number to the power 1 by 3. Okay. So, if you calculate it, you will get as 259.3. So, H bar you can calculate 259.3 into K. Okay. Thermal conductivity is 28.08 divided by L, L is 1.2. So, H bar will be 6.067 watt per meter square Kelvin. Now, let us calculate the heat transfer rate due to convection. Okay. Heat transfer rate due to convection, you know it is H bar into A into T W minus T infinity. Okay. So, what will be your area? So, H bar already we have calculated, it is 6.067. Okay. Area will be both side we need to consider. So, 2 into 0.6. Okay. Meter is the length and width is 1.2 meter. So, this is the area. So, both side we are considering into T W minus T infinity. So, 95 degree centigrade minus 25 degree centigrade. So, if you calculate, it will come 6.067 into 1.44 into 70. So, it will come as 61, it will come as 611.55. So, you can write it as 612 watt. Okay. Now, let us calculate the heat transfer due to, now let us calculate the heat transfer rate due to radiation. Okay. So, you know you can write it as sigma, which is your Stefan Boltzmann constant, into emissivity into heat transfer area into T w to the power 4 minus T infinity to the power 4. Okay. So, in this case this T you need to take in Kelvin, because in radiation we know that the temperature you have to use in Kelvin. So, now sigma is your 5.6704 into 10 to the power minus 8. Okay. Emissivity is 0.9. Okay, it is given in the question. Heat transfer area is 2 into 0.6 into 1.2, and now this temperature you have to use in Kelvin. So, 273 plus 95 to the power 4 minus 273 plus 25 to the power 4. Okay. So, if you calculate it, it will come as 5.6704 into 10 to the power minus 8 into 0.9, this is 1.44, and if you calculate it, you will get it as 1.0454 into 10 to the power 10. So, it will come around 768.21. So, let us take at 768 watt. So, you see this is heat transfer rate due to convection, this is heat transfer rate due to radiation. So, that total heat transfer rate will be Q total will be Q convection plus Q radiation. So, this is your 612 plus 768. So, it will be 1380 watt. So, now let us discuss about the last problem. Air at a temperature of T infinity flows over a flat plate with a stream velocity of u infinity. The plate is maintained at a constant temperature of T w. The velocity and temperature of air at any location are given by, this is your u by u infinity, and this is your T minus T w divided by T infinity minus T w, where y is the distance measured from the plate along its normal, and delta T are the hydrodynamic and thermal boundary layer thickness. Find the ratio of heat transfer coefficient to shear stress at the plate surface using the following data. So, you can see in this particular case your velocity distribution and temperature distribution are given. Okay. So, now we have to calculate the ratio of heat transfer coefficient to the shear stress. Okay. So, as you know velocity distribution, you will be able to calculate the shear stress, and temperature distribution you know. So, you calculate the heat transfer coefficient and make the ratio. Shear stress at the wall tau w is mu del u by del y at y is equal to 0. So, this is your u by infinity. So, this if you see mu into del u by del y. So, it will be u infinity into pi by 2 delta into cos pi by 2 y by delta at y is equal to 0. Okay. So, if you calculate this, tau w will get as mu into pi u infinity by 2 delta. Okay. Now, heat transfer coefficient you can calculate as H is equal to minus k del T by del y at y is equal to 0 divided by T w minus T infinity. Okay. So, this is the temperature distribution. If you calculate del T by del y at y is equal to 0, then you will get minus k T infinity minus T w divided by T w minus T infinity. Okay. And at y is equal to 0, if you put, then after taking the derivative with respect to y, you will get 2 by delta t. Okay. And you see this is T infinity minus T w. If you write in terms of T w minus T infinity, then it will become plus and it will get cancelled. So, you will get twice k by delta t. Okay. So, now we need to calculate the ratio of H by tau W. Okay. So, H is your twice k by delta T and tau W we can write 2 delta divided by mu pi u infinity. Okay. So, you will be able to see this as 4 k divided by mu pi u infinity into delta by delta t, and delta by delta t you see it is given as Prandtl number to the power 1 by 3. Okay. So, you can write as 4 k divided by mu pi u infinity Prandtl number to the power 1 by 3. Okay. So, for this particular case Prandtl number you can calculate mu Cp by k. So, mu is 2.5 into 10 to the power minus 5 into Cp, Cp is 1000 joule per kg Kelvin. So, this is your 1000 divided by k, k is your thermal conductivity, this is your 0.04. Okay. So, 0.04. So, if you see this, if you calculate you will get 0.625. So, H by tau W will be your 4 into thermal conductivity is 0.04 into Prandtl number to the power 1 by 3 divided by mu. So, mu is given as 2.5 into 10 to the power minus 5, then pi into u infinity. So, u infinity is given as 10 meter per second. Okay. So, this is into 10. So, if you calculate it you will get as 174.18 meter per second into Kelvin.
So, now we have found the ratio of heat transfer coefficient to the shear stress, okay, at the wall. Thank you.